So, ladies and gentlemen, I really highly appreciate that I'm here to present a new IO-Link technology here that we are trying to position to the market. My name is Karim Jamal, as you see, and I'm just gonna report what our new task force for IO-Link Plus is doing. I hope that we don't have anybody in the room or remotely that still have questions. What does this mean, IO-Link Plus? I guess it's clear, right? We had lots of discussions in the past. What does this mean? Is it single pair Ethernet? Is Ethernet? Is it a new protocol? What does this mean? At the end of the day, we did get together and we did put kind of positioning paper, which is available for all IO-Link members. In this positioning paper, we did highlight basically that we are not going to replace IO-Link. That's number one. We are extending IO-Link for some use cases. That should be clear for everybody. And based on that, we say, okay, which kind of enhancements are we targeting to achieve with IO-Link Plus? Number one was basically the distance coverage or length. As you know, IO-Link is limited to 20 meters right now. And if we want to do better, well, single pair Ethernet as one physical possibility can do the job. And second, we talked about the power. So here we have options and we can do better. We can do the same like IO-Link today. And of course, we are moving from 3 wires to single pair Ethernet. If you use single pair Ethernet for IO-Link Plus, meaning that we're going to move also to 2 wires. That was the next one. This is a table, by the way, you find it in positioning paper. And one big important wish from marketing from beginning was unshielded cable. And you're gonna agree that unshielded cable in terms of ease of use, in terms of cost, is really one differentiation for IO-Link today, right? And the task force was basically requested to verify if we can do the same with IO-Link Plus. This is number one for the physical layer task force. The other thing was basically the special Class B port, which has today additional power solution. And we're going to see also that for IO-Link Plus is the same. And we have, of course, some doubts. How can we improve, basically, because we are getting now 10 megabits per second bandwidth. How can we improve, basically, the protocol themselves for it? Because there are use cases that requires more data bandwidth, maybe less jitter, and we can use this new physics to allow IO-Link Plus to do the job for new use cases. That was basically the first slide, and I want to call it just the mission for IO-Link Plus. And based on that, we started our engineering activities. That is task number one for us as task force. We split it basically the working groups to 2 working groups. We have really motivated engineers, and thanks to the companies that they really engaged this way to do this amazing job here for IO-Link. And at that stage, I want to take this opportunity to ask all companies, all members, to engage for this new feature. Because this is really something specific for us, and we have to make it good. And if we do it good together, that will be the next step for IO-Link. That was basically the mission for the task force. As I mentioned, we split it to 2 groups. We have physical group, taking care of the hardware-related stuff, like the PHY, cable, connectors, power implementation. And we have another group which is basically focusing on the protocol itself like ODD and basically the package, the frame, all this stuff. We started with the power, and it was honestly easy go for us. We don't want to define something new. We just take a look what exists, and we want to make sure that what we are using for IO-Link is stable, robust, and validated. And of course, we have standards. PODL, for example, And before we moved to Podl, we took the decision based on the positioning paper to concentrate and focus on 10-base T1L. And T1L, because we have really point-to-point protocol in front of us, right? That was also kind of first decision for IO-Link Plus. Based on that, we did take a look basically on the table 104-1A classes. And it was for engineering, or for all engineers, very easy to figure out that basically between 10 and 12, we fulfill the requirements for IO-Link Plus. So there is no challenge. We can do it for port A. It's given. And surprising, it's not surprising, but it's amazing that the other groups in parallel, like process automation APL, for non-safe use cases, they came to the same point. So there is kind of harmonization between what we are doing in terms of power, non-safe, with between IO-Link Plus and APL process automation as well. The good thing is, for any member, any IO-Link member who would like to start testing or checking the feasibility of Podl for IO-Link, we have reference designs. So there are references designs available that you can just use, and pretty easy basically for the start of evaluation. The only thing we did skip at the beginning is basically the port B, power for port B, and how can we make it. This is basically the next step for the Taskforce physical layer. That was the first task for this sub-working group. The second task was basically the unshielded cable. And I mentioned from beginning, this is a really kind of differentiation, and we have been basically requested and asked to make sure that we test all aspects and make sure that we can fulfill these requirements. Therefore, we did align first basically on the test plan and specification. To make clear that's basically if we have different test centers, they are testing the same way. And for that, we got some volunteers. So we had basically two, let me say, major partners working together. One center was Weidmuller and Phoenix Contacts and Rosenberger. That was center number one. And sensor number two, as test sensor, was basically Harting and Leone as the second one. And Texas Instruments in Freising did kind of preliminary testing in their lab as well, so that we have kind of three different inputs based on the same test plan, based on the same test specification, to make sure that we cover everything required. So, in terms of test plan, there is a test plan available that will be also uploaded shortly to the IO-Link server, so you can take a look on it. And in terms of hardware, from beginning, we are making sure that we have kind of second source. So we don't use just one hardware setup. At least we need to have two different setups to make sure that our results are valid and can be representative. Of course, the module should be 10-base T1L, as I mentioned from beginning, because we did focus on that one. So we took just two available AVMs right now for 10-base T1L. One is from EDI, and the other one is from TI, from Texas Instruments, as FICE, as module, as AVM that can basically base our hardware testing on it. The cable, and again here, thanks also to cable manufacturers and all companies, even IFM did provide another cable for testing. Thank you for that. And we need really such kind of help and support for our task force. For cable, we have two different cables. And I can tell you, all existing solutions today for single pair Ethernet, they are based on shielded cable. Automotive is shielded cable. And APL, process automation, is going shielded cable. So unshielded cable, if we make it through, will be really differentiation for IO-Link. Will be unique. IO-Link, the only one who is driving unshielded cable as infrastructure. So we did this job, and this is just engineering job with first results. To make it clear before we move to AMC and impact, in terms of communication point to point, there is no issue. There is no link drop. There is no issue that we can report and say, okay, the communication is not working. In temperature room, of course, test labs, everything passed very well. But in terms of AMC and robustness and electromagnetic environments aspects, we did pass, as you see here, with unshielded cable, the E1, category E1. But we did fail for E2 and E3. That is the status today. That's what has been observed from 3 centers, but it's not like final solution. So we are trying to figure out, is there something we can do to make it real, to make it happen? It's still in discussion, and we're going to come back to steering committee as next to figure out if we're going to engage somebody else to do maybe to verify the aspect, the background of testing. But if it is as it is, we're going to be like others on shielded twisted pair and not on unshielded twisted pair, if it stay this way. If you have questions to that topic here, we're going to have a little bit time for open questions. The other sub-working group, which is dealing with the protocol itself, honestly, it is easy go. I don't see any blocking points. Things are really moving smooth and forward. So for us, it was clear that we are not going to change IO-Link. IO-Link will stay IO-Link with all channels that are known. There will be no changes. This is number one. The content in terms of cyclic and acyclic data will be the same. So we are following IO-Link standards. We are not doing something different. We are not doing Ethernet. We are doing IO-Link. This is number one. The other thing is we did figure out from beginning that's basically the packet length, even defined in positioning paper, we have kind of window, and that can vary between device and master. So we are not limited basically to do the same packet length. And for real time and to basically grant, let me say, predefined transmission time and receive time, we avoid basically any kind of segmentation for the frame, at least for the process data. The other topic that's big, and maybe I can tell you why we did deal with the possible master architecture. You can ask me and say, well, Karim, normally this is a part for the other group, it's not for the make layer group. But I'm happy that the subgroup make layer did the job, because the topic latency, for example, and point-to-point communication in terms of timing is related to the setup, to the architecture you choose for it. I know it's point-to-point, we are talking device to master, but the implementation of master can be different. Even the PHYs that we are using as single-pair Ethernet, they have 2 different interfaces. There are PHYs that integrate basically MAC, and they just use SPI to talk to microcontroller or to FPGA or MPU. And there are PHYs, they are talking MIIs. 2 different interfaces, 2 different schemes and timings we should take care of. This is number one. Number two, in terms of cost perspective, we have to figure out which architecture would make sense and keep IO-Link kind of production floor number one selection. But it was clear for the team, it was even from positioning paper pretty clear that we are not going to change the word. We are going to use the Emacs as SDR, as they are implemented. We are not going to do something different on B or B, let me say, related to just one solution, on one priority solution. We want to avoid it because IO-Link is global, IO-Link is broadly, and we want to make it the same way. That's why we are basing all engineering testing and concepts on standards image that you can find in any microcontroller, or standards image that is basically integrated in the PHY itself. And yeah, if you remember the first paper studies that have been published before the task force has been created, Dimitri and Hadmut did this job before. We were thinking to make it easy, just basically tunneling the IO-Link frame as it is in a standard Ethernet frame. And we did pass this one. We did talk about it, and we come to the point, and Dimitri is here also in the room, we come to the point where we did say, we have to adapt really this frame for IO-Link to make it IO-Link. We are not forced to be Ethernet. Is it standard Ethernet? Yes, as physical layer, right? But the frame itself should be somehow defined in a way that fits to our IO-Link protocol and to our requirements. And this is what the team is doing. And here we are talking about frame structures. We are talking basically about link, transmit and receive schemes, how the device should talk to master, how acknowledge, and all this stuff. This is where the make layer or the performance group is right now working on it. So this is the general status where we are today. So remember, we have basically from physical layer, we have just one challenge right now, how we make unshielded cable valid for IO-Link Plus. This is open right now. Results mentions SCP will be better, shielded will be better in terms of AMC. In make layer, the protocol group, we are moving forward. I don't see any issue of basically drawing the first spec or concept. That brings me to the last slide. What is next? So number one, we're gonna get together back with marketing team to estimate basically the facts, the results that we have from physical group, based on the results for unshielded cable. We want to do something specific as IO-Link, and we believe on unshielded as differentiator, and it should be there. If yes, we're going to do all possibilities to make it happen if the physics gives us the possibility. If the physics is against all stuff, and it will be possible, but it makes it really expensive, that is where we need marketing inputs and selling community feedback. The other thing is, we see already today that we can do more. That's what we are trying to do. This is a really start of something good and future of IO-Link. Meaning, we have to ask ourselves, we reuse what exists for IO-Link as successful protocol for production floor, or we're going to do more of that. The time is now ready for it. Yeah, and of course, if we clarify those two topics, do it different, do it IO-Link specific, make it happen, we're going to come to the spec, the first draft, and we're going to move to the start of test and evaluation. That is the status right now for this task force. Time, not sure.
It's okay.
Any question before I leave the stage?
Yes, any questions?
On your slide 6, there's a second source of PHY with usage at Emacs. Why is necessary?
So yes, I remember the slide. So you're right. There are two PHYs available from ADI. You mean the PHY from ADI, right?
Yeah, and what is behind Emac? What is it?
Just as a Mac. Also, it's not just the PHY itself. It's basically the Mac is included. Oh. So you don't need the Mac, and the microcontroller is included in the PHY itself. Okay. So ADI has basically two PHYs available today. One is using MII without Emac integration, and the other one is having Mac, and you can just use SPI to the microcontroller. Any other question?
Any other questions? Okay, thank you, Karim.